Hello once again. This is going to be the last theoretical section on the node voltage method, and then we're actually going to dive into a few examples. I know it's quite a bit of material, but trust me, it will pay off because it's one of the most powerful techniques of circuit analysis that we actually have. So this is a continuation again of section 4.2, and this I'm going to title the node voltage method. And I'll call it a recipe. Now, if you happen to follow this recipe, about 90% of the problems that you encounter in the textbook will be solvable if you faithfully follow the recipe. However, from time to time, depending on the circuit, the recipe might be a little bit more complicated to use compared to other techniques. So you do actually need to know this recipe pretty inside and out to be able to use it faithfully, consistently. But let's go through this kind of step by step. And in the first step in the recipe is to select a ground node. Now, you can choose any node whatsoever that you want as the ground node, but as we'll see as we go through examples, some ground nodes lead to more work than other ground nodes. And it's only through practice that you actually start gaining a feel for which node is the best node to choose as the ground node. In general, it's usually the node that has the largest number of circuit elements hooked up to it, but not always. So we select this ground node and assign it a node voltage of 0. Next, what we want to do is we want to identify independent nodes and label them. Now, you might question, justifiably so, you've talked about a lot of different types of nodes, but you never mentioned what an independent node is. And an independent node is a node where the voltage is unknown. So this is a node where the node voltage is unknown. This is really tantamount or equivalent to defining your circuit variables for your system of equations. And the way we're going to identify the independent nodes is very specifically by looking. So do this by looking. Let's change that. At all the voltage sources. So every node, every essential node will be independent, right? And as soon as you start taking a look at the voltage sources, for each voltage source that you have, one of those nodes is going to be dependent. So the voltage sources will reduce the number of variables that you have within your system every single time by one. The next thing that we're going to do in our recipe is we are going to assume that all the currents at every node are flowing out of the node. And none are flowing in. Now, I want to bring your attention to the word assume. This is a convention. So in parentheses, this is a convention used for bookkeeping purposes or keeping signs straight. Right? Our book assumes that for every node, the currents are flowing out of the node, that there are no currents flowing in. Different books will have different conventions, but this is the one that we will consistently stick with. Right? This also means that KCL, which tells us that the sum of all of the currents flowing out of a node equals the sum of the currents flowing into the node. Well, if none are flowing in, that means that this is equal to 0, and KCL simplifies, right? So we're actually going to use this version of KCL every single time we use the node voltage method. But we are going to use KCL and Ohm's law to set up a system of equations in terms of the node voltages. The next is relatively simple. Solve for the node voltages in your system. And you can use any technique of mathematical analysis that you want. You can use Gaussian elimination, you can use substitution, you can use matrix methods. For me personally, I tend to use a calculator. I have a calculator capable of handling these types of calculations for me. So once I know I have a complete system of equations, I throw them into the calculator to get my solutions for the node voltages. And then the last step, and this is one that's sometimes overlooked by people, is, well, sometimes you're not looking for voltage, right? Sometimes maybe you're looking for a current or a power. Well, you're actually going to use the node voltages to find whatever desired quantity you want. So here we are going to use the node voltages to find the desired electrical quantity. So this is it, total of 5 steps. And we will see through examples how these steps can actually be used in order to analyze circuits.